Welcome, everyone, to day 3 of the fall 2021 Martin Gardner Celebration of Mind Talks. We are very pleased to have Rachel Quinlan, who is a mathematician at the National University of Ireland in Galway. She mostly studies combinatorial aspects of matrix theory and linear algebra, but today she's going to be talking to us about origami and the wallpaper groups, which I think is a very cool connection. I've seen some of her samples. They're really neat. Also, she was recently completed a term as the head of the School of Mathematics, Statistics, and Applied Mathematics in Galway, and was the first woman to hold that position.
Great. Thank you so much, Bob, for that lovely introduction. And thank you, everybody, for being here. I'm so delighted to be a part of this event. It's been absolutely wonderful so far. I've enjoyed every talk that I've been able to go to with the time difference. And it's just been a real pleasure to be part of this wonderful event. So I'm so grateful to the organizers for organizing this super event, and also of course for inviting me. And I'm very excited to speak to everybody about my mathematical hobby rather than my mathematical research, and that is origami. So here, hopefully you can see the slides. If not, please put a note in the chat. And what you can see here are 4 photographs of 4 pieces of paper. Each of them is folded many times, and each of them is a piece of paper of just one single sort of consistent color. And the differences in color that you can see in each picture are just because the pictures are lit from behind. They're just stuck onto a window. So the light is coming from behind, and the places where the color looks darker is just where there are multiple layers of paper, and the brightest areas are where there's only a single layer of paper. And so I guess with these pictures, we can observe that all of them look like sort of periodic tilings of the plane, in the sense that each of them has sort of basic blocks that are repeated and that together cover the entire plane without overlaps. So they're examples of tessellations of the plane. The first 3 of them maybe look a bit alike, and again, that is not if you've noticed that, you're right. And in particular, maybe this will be important later, we can observe that all of them have these little hexagons like this. And so all of them have these hexagons that are surrounded by various different kind of decorations. But all the first 3 have those sort of hexagons that appear more or less in the same places. One of them actually is a little bit obscured there, but that's supposed to be a hexagon. And so this yellow one, the blue one, and this kind of orange one, all are sort of close relatives of each other, even though they don't look especially similar. And that's one of the things that I'd like to talk about. The 4th one here is based on a sort of a square grid rather than a triangular or hexagonal grid. So it's not as close a relative of the other 3, but it does have some other relatives that I'll try to say something about as we continue. Okay, so a few words about wallpaper patterns. So the wallpaper groups classify the distinct systems of symmetry that can occur in a periodic tiling of the plane. And by tiling, I just mean tiling, like tiling your floor, a covering of the plane with non-overlapping, identical and identically oriented pieces, be they squares or hexagons or some other shape, whatever they might be. So in a wallpaper pattern, we have translations in 2 independent directions. So maybe vertical and horizontal if it's a tiling with squares, but they don't have, but the angle between them can be anything except 0, I guess. And so we have this kind of system of translational symmetries within the wallpaper pattern. That might be the entire story. There might not be any other symmetries besides the translations, in which case the group of symmetries is a free abelian group of rank 2, but in any case, it always has this system of translations within it. There may also be further symmetries. For example, there could be rotational symmetries of the entire tiling. If so, the famous crystallographic restriction theorem, which I've misspelled there, I see, tells us that any rotational symmetries that do exist in the pattern can only have order 1, 2, 3, 4, or 6. So there can be rotations through 180, 360, 120, 90 degrees, or 60 degrees. They can be 6-fold, 4-fold, 3-fold, or 2-fold rotations. So the crystallographic restriction, I won't get into it too much here. I think it's an example of a kind of a deep fact that has an elementary proof. It's really, it really sort of governs so much of this sort of periodic geometry of 2-dimensional space, and also, of course, in 3 dimensions. So within the language of this topic of tilings, a primitive cell is a basic tile. So it's a minimal tile that through its translated copies covers the entire plane. So in this particular picture, this is a photograph again of an origami tessellation on a piece of paper. And here, this square would be an example of a primitive cell, because by translating this square around, we can translate it up here, we cover the next sort of bright square there, we can translate it down here, and so on. And we can cover the entire area just with translated copies of that square. So really, this is a sort of, you know, it's a tiling with squares of the plane. But in this particular pattern, we can also observe that there are other symmetries besides the translations. So for example, there's a reflection in this vertical axis. There are reflections in the horizontal axes, which are the diagonals of the sort of basic tiles. There are rotational symmetries, fourfold rotational symmetries about the center of each tile, and also about this point where four of these primitive cells meet. And there are also reflections in the lines that pass through the midpoints of the sides of the tiles. So this is an example where, in fact, every symmetry of a basic tile is also a symmetry of the entire pattern. We can, if we take that highlighted tile as being sort of the basic one, we can reflect the whole pattern in that vertical line, or the horizontal one, or either of the two diagonally oriented lines that pass through the midpoints of the squares of the sides of the square. So we don't need so much of this lingo, but just to mention that it's come up already in a couple of talks, that a fundamental domain is a term that we'll use for a minimal region that generates the entire pattern through its images under all symmetries, not just translations. So in this particular picture, for example, this red triangle would be a fundamental domain, because if we reflect that red triangle, for example, in this line, we fill it out to this quarter of the square. If we then rotate through all the rotations about the center of the square, we can fill up the whole square. And once we've done that, we can use the translations to fill out the rest of the picture, for example. So there's a slight distinction between a primitive cell, which is a sort of the basic tile, and a fundamental domain, which if you allow yourself to also perform all the rotational and reflectional symmetries, would give you the whole pattern as you proceed, as you spread it around the picture. Okay, so the reason why the 3, 4, or 6 are highlighted here is because in this talk, I'm going to focus on the examples of tessellations, or periodic tilings of the plane, that have rotations of order 6, 4, or 3. We're going to start with 6 and 3 first, and then at the end we'll have a look at some that have order 4. Okay, so if we want to think about what a periodic pattern with 6-fold rotations might look like, let's just kind of think about the symmetries that would have to be involved, and figure out how much we can figure out. So we're going to start with this point, which we're going to consider to be a center of 6-fold rotational symmetry. So we're going to create a periodic pattern that has 6-fold rotational symmetry, so 60-degree symmetry about that point. And we're going to introduce another 6-fold rotation center, which we're going to assume we're assuming that the distance between these two is the shortest distance between any pair of 6-fold rotation centers in the whole pattern. So there are no pair that are nearer to each other than those two. And if we do that, then the knowledge that these are 6-fold rotation centers tells us where we can expect to find more of them. So for example, rotation through 60 degrees about this point, this blue one, should be a symmetry of the whole picture. And same for, we could repeat that. So all these red points also must be 6-fold rotation centers. And there are no more inside this hexagon, because none can be closer to the blue one than these red ones are, and so on. We can continue that story, and we get this kind of triangular lattice of points, which all must be 6-fold rotation centers. Okay, if we develop this a little bit more, then I'll ask you to kind of take my word for this for the moment, but you can figure it out later if you have time. That by composing rotations through 60 degrees and multiples of 60 degrees about different points, we can establish also that there must be a translation of the entire picture, which is a composition of rotations that takes us from the red point, from this blue point, to the red one, for example, and that just sort of moves one step right in this picture, and so on for all the rest, which tells us that if we just fill in these triangles, that all the blue triangles must be translates of each other, and the same for all the white triangles in the entire picture. And the assumption here is not that our tiling consists of plain blue and plain white tiles or anything like that. We're not assuming anything about what decorations might be upon these triangular tiles, or whether, for example, they have their own, whether they have further symmetry than what we can see here, or whether they have all the symmetry that we can see here. We're just saying that, that this is sort of the pattern of rotation centers and the translation lattice. Okay, so all of these sort of unit vectors, I guess, are translations in the pattern. And then also, by composing short translations with 60-degree rotations, we can also establish that the center of each of these triangles, the white ones and the blue ones, must be threefold symmetry centers. So I'm not saying that this should be obvious at a glance, but a little bit of messing around with composing translations and rotations that we already have does establish that for us. Okay, so let me just advance it over. Oops. Yeah, so at this point, we can say that this parallelogram, which is highlighted in this kind of green color, is a primitive cell for the tiling. Through its translates, it covers the whole plane. Also, the center of each triangle is a threefold rotation center, which tells us at worst that this kind of kite region is a fundamental domain, and that through its rotations of order 3 about this point, which is a threefold rotation center, it covers this triangle. And then once we have that triangle, we have all the rest through rotations. Now, it may be that that's the entire kind of symmetry system that occurs in this pattern. It may be that we also have reflections. So for example, reflections in the medians of any of these triangles could be symmetries of the entire system. If any of them are, then all of them are, because they can be composed with the rotations to 60 degrees and 120 degrees. So basically, if for example, this vertical line is a line of reflection in the pattern, so that would be saying that this tile, this blue triangular tile, has an axis of reflectional symmetry here, then it will also be true from composition of that reflection with all the rotations that all the other medians of every triangle will also be lines of reflectional symmetry, and also the boundaries between adjacent triangles. So it could be that we have all those reflections, or it could be that we don't have any of them, and we just have the rotations. And those are essentially the two possibilities for wallpaper systems that do have six-fold rotations. I want to talk about origami as well as about wallpaper groups. So let me show you, let me come back to these two examples. So it does turn out that these are in fact the two cases that can arise, and these two origami tessellations actually realize those two patterns. So the notation for wallpaper groups, there are various notations for them. The one that's mentioned here is the so-called crystallographic notation. It's not the most appealing at first glance if you haven't seen it before, maybe. So let me just say that the 6 in both cases refers to the fact that we have six-fold rotational symmetries. The M in the first case, M is for mirror, and it refers to the fact that we also have reflections in the first example. And the P6 without any further notation after that. In the second case, it tells us we have six-fold rotations, but that we don't have reflections. So these two tessellations look somewhat alike. I mean, they have the same, they both have the hexagons, which are the six-fold rotational symmetry centers. And they both have these kind of, I don't know what to call them, these kind of three-legged things, these little kind of triangular things or whatever, which are the threefold symmetry centers. So the centers of these gadgets are centers of threefold rotation for the entire pattern, and that's true in both versions of the picture. In the version on the left, we can highlight a primitive cell in each case, and in the version on the left, we can see, for example, that the two triangles on the left and right-hand sides of that primitive cell are images of each other under a reflection in the vertical axis there. And on the left-hand side, we can say that that's not the case. These two are not images of each other. The vertical axis there through the primitive cell is not an axis of symmetry of that parallelogram. And we can also observe in the picture on the left, maybe I'll go back to the case, so this version of it shows the axes of reflectional symmetry, at least on one side, and of course all their translates are axes of reflection as well. But we can observe that, you know, the symmetry group of this triangle, and also of every other triangle in the picture, is the full dihedral group, D6. So all the reflections and all the rotations of that triangle are symmetries of the entire picture. That's not the case over here. We only have the rotations. Okay, so I guess, I mean, okay, so I'm interested in making these origami tessellations, but I kind of became interested in the question of, you know, how can you kind of adjust an origami pattern from one wallpaper group to another? Because all of these little colored dark areas, you know, they're areas where there are kind of multiple layers of paper. And in some cases, they can be moved a bit without having to do a whole reconstruction of the entire pattern. And maybe you can move from one pattern to another. And so you could ask yourself, like, what do you have to do to this pattern on the left in order to kill off the reflections and only keep the rotations, for instance? And if we look at this kind of hexagon here in the center, which is repeated obviously all around, maybe we look at this one because it's not partly highlighted. So I'm just looking at this kind of inner hexagon, which has this center bright hexagon with these kind of decorations around it. And the difference really between that hexagon on the left and the one on the right is that the little kind of diamondy things around it are sort of offset in the second picture, so that they sort of respect the rotation, but not the reflections anymore. So I would like to kind of try to show you how that's done by actually doing it here live on air. And the other thing I want to remark, so these two pictures are created from a pre-creased triangular grid with triangle twists and pleat intersections. So I'd like to try to explain what that means. So this is a pre-creased triangle grid. So it's just a square of paper, which is folded into these triangles. So it's got a full sort of triangular lattice. So the first step in creating any of these origami designs is to fold a pre-creased triangular grid. And this is kind of the necessary but not glamorous part of the job. It takes a bit of time and it takes a bit of practice to do it accurately. And but the one thing that inaccuracies at this stage will certainly cost you later in terms of your completed design. Okay, so a pre-creased triangular grid is what you're looking at here. A triangular twist and pleat intersection. Well, let me tell you first what a pleat is. So a pleat is, if we lift up just kind of one sort of layer here of our grid, we can fold it down. So here the dark part has 3 layers of paper and everything else has 1. That's a pleat. And a pleat intersection is if we make 2 of those intersect, or 3 of them really intersect, making kind of a 120-degree angle with each other. Okay, and so that's a pleat intersection. And one way to make that kind of lie down flat is to just fold it like this, which happens many times in both of these pictures that we were looking at. And that's very nice. And that features prominently in all of the pictures you're going to see, most of them that you're going to see today. But a triangle twist is one of my favorite things. So let me show you what that is. So if we just hold up the 3 pleats again, so they're sitting above the page, and they make a sort of triangle with 3 sort of 3 kind of spokes of this wheel are sitting above, vertically above the page. And I can put my fingers, let me try to turn down the light a little bit maybe. So they're sitting kind of above the page like that. And I can put my fingers on the 3 corners. And just so this, it's kind of they're sitting a bit above the paper, not right on top of it. So I can just exert a little bit of pressure. And what happens when I do is the paper just starts to spread out at the top. And I can keep doing that until it sort of folds right down into a triangular shape. And then I can flatten it down. So that is what a triangle twist is. And it is one of my absolute favorite things. If I have a bad day, I do a few triangle twists and that improves the situation. So that's a triangle twist. And paper is just the most extraordinary material. I think there are some things that are so everyday and so commonplace that we forget how extraordinary they are. Paper is one of them. I mean, it has the most extraordinary mechanical properties. What else could you do this with? What other material? It's just rigid enough to sort of sit up above the page like that in the pre-twisted form, and just pliable enough to kind of fold out in this controlled way when you exert the pressure at the 3 points. It's also, it has extraordinary properties when you fold it as well. You can fold it in a hard crease and you can unfold it, but it retains a memory of the crease. And that's one of the things that makes origami work. And of course, paper has, such importance also in our history and our culture and so on. It's really such a special material. It's durable and pliable, but it's mostly an organic material. It's just it's extraordinary stuff. Other things that are extraordinary are water and cubes. They have just extraordinary properties, but they're so everyday that we can easily sort of forget that. So there's the triangle twist, and here it is. Here it is backlit. So you can see it just sort of sitting there above the page. Okay, that's a triangle twist. So I claim that I'm going to show you how we can go from the P6M pattern to the P6 pattern. So what you're looking at here is a version of the yellow picture that we saw earlier. And here, for example, we have like one of those sort of hexagons, surrounded by the 3 rotation centers of order 3. And around each of the hexagons, we have these little kind of decoration of little kind of bright diamonds and triangles. And those are essentially formed from triangle twists. And they're formed from pairs of triangle twists that are folded over. So if we wanted to go from this version to the version that doesn't have the reflections anymore, but only has the rotational symmetries, a way to do it is to just take each of these sort of flaps at the edge of the central hexagon and just fold it over so that the brightly illuminated part kind of moves from the center over to the edge. Do it all the way around. And we see our hexagon with full hexagonal symmetries kind of turning into a hexagon that only has the rotational symmetries. I have to do that one again. Just have to fold them down a bit harder. So that's exactly how to go from the yellow picture to the blue one. And I suppose the other remark that I would make about paper is that you can fold it so well, it's so sort of reliably foldable. And you can also unfold it, and you can make sort of small adjustments to these folds, which makes it really sort of, I think, useful for exploring the different wallpaper groups and the relationships between them. Of course, you can do this by drawing pictures, and people do the most extraordinarily beautiful pictures of all these symmetry patterns. But I think, you know, the tactile nature of paper and the fact that you can reverse your steps makes it really valuable for that. That's the examples with the 6-fold symmetry. So if you want some examples with 3-fold but not 6-fold symmetry, okay, so, and again, we can sort of figure out what the pattern of 3-fold centers looks like. So there's 2 more of them there coming from rotating the first red one around the blue one. 3 more, these are all translations, so their negatives have to be translations as well, and we can fill out the whole picture with 3-fold rotation centers. And remember here, we're thinking about patterns that have a 3-fold, but don't have a 6-fold rotation center. So again, if we fill in the triangles here, what we're saying is that the rotation to 60 degrees that would take this yellow triangle onto the white one, we don't want that to be a symmetry of the picture. So the yellow and white triangles are different from each other in the sense that rotating the yellow one onto the white one doesn't give you a symmetry. So they're decorated differently, or they could be different colors or whatever. So as this picture as it stands, if we interpret the colors as indicating a difference, which would have 3-fold but not 6-fold rotational symmetry. Okay, so that's basically sort of the picture of where the sort of translation images of the original blue 3-fold center is. We can discover also from combining rotations that all the centers of all these triangles must also be 3-fold rotational centers, though not necessarily images of each other under translations. And then we have the question of whether any reflections occur or not. And so it is possible, you know, of course, any line of reflection must be a line of reflection of the lattice of translations. So for example, the medians of the triangles could be lines of reflection. If this green one is, then the other 2 green ones must be as well, because of the rotational symmetries that we know occur through 120 degrees. Alternatively, it could be that we have lines of reflection kind of passing along the boundaries between adjacent triangles, like which are indicated here in red. But if we're trying to describe patterns that have 3-fold symmetry, but not 6-fold symmetry, then we can't have both the red ones and the green ones. Because if we had 2 lines of reflection making an angle of 30 degrees with each other, then we would have a rotation through 60 degrees coming from their composition. So essentially here we have 3 possibilities for what the systems of reflections can be. We could potentially have no reflections and only all these 3-fold rotations. We could have the reflections in the green lines, which would say that all of the triangular tiles, the yellow ones and the white ones, all have sort of their own reflections within the, like with the, you know, the reflection of any triangle is a symmetry of the entire tessellations, but that the yellow ones and white ones are not images of each other. So they could both separately have kind of patterns that respect the symmetry of a triangle. Or we could have the red lines of symmetry. And that would be saying that the yellow triangle itself doesn't have reflections. It has some decoration on the tile that doesn't permit reflections, but that the yellow and adjacent white triangles are images of each other under reflections. And again, all 3 of these possibilities can occur. So, and they correspond to 3 more wallpaper groups, which are called P3M1, P31M, and P3 in the crystallographic notation. Indicate these pictures. So these again are all close relatives of each other. The 2 on top are our friends P6M and P6. This one is the wallpaper group for what they call P3M1. And if we look at the fundamental or primitive regions or primitive cells in each of these, we can observe in this kind of brown or orange one that the primitive cell again is a parallelogram with 2 sort of triangular halves on the left and right, if we look at it that way. Each of those 2 triangles, if you imagine a vertical line through the center of this parallelogram, each triangle has all the symmetry of an equilateral triangle. but they're not the same as each other. This one has a little triangle at the center, and this one has this sort of three-pointed or three-legged thing. So this represents the group P3M1. M is for mirror, again, indicating that there are some reflections there. Okay, and again, you might notice that the hexagons in this picture are kind of in the same positions as the hexagons in the yellow picture above it, and also that these three-legged things appear not with the same frequency. We don't have 6 of them around every hexagon, but only 3 of them. But they do also kind of resemble the ones that appear up here. This one is for the group P3, which has rotations, but no reflections at all. It has rotations of order 3, and the centers of threefold rotation are the hexagons. And again, these are the same hexagons that we have up there and up here. And we have them with the same frequency, in all these pictures. So all the hexagons in all the pictures are in the same positions. We have some of these three-legged symmetry centers, like this one is here, it's also there. And we have another one, a different one. It's kind of skew. So it still has threefold rotational symmetry, but it doesn't have reflections. And we have these kind of semicircular things that have appeared that weren't there before. This is an example for the group P31M, which is the one where the triangles have only the rotational symmetry and are mirror images of each other. So here the primitive cell is a bit bigger, but if you look at it, you can sort of hopefully notice that if you look at the left-hand triangle here, it has threefold rotational symmetry, and you can kind of see that in this kind of these little 3 legs that sort of turn out here. And the 2 sides, the 2 triangles, are images of each other in the line that passes between them. But the triangles themselves don't have reflections, which are symmetries of the entire picture. So that's the group P31M. The notation is not the most friendly when you first see it, I think, but that's what they call this group. So so these are all again close relatives of the original yellow one that we started with, and in fact it's exactly the same piece of paper. This one here, the yellow one and the yellow one up there that we started with. So that one on the top left has now sort of morphed into the one in the lower right, but all the others are relatives of it. So just as we did before, let me try to show you a little bit about how that works. So for example, maybe I won't go through all of them because I don't want to take up your whole evening, but let me show you how to go, for example, from the P6M, which is the yellow one, to this P3M1, which is this one with the kind of opposite triangles, which both have the full triangular symmetry, but are not mirror images of each other. So for that, apologies for all the back and forth, but I'm going to go back to the camera. So here again, okay, so this is a copy of the yellow P6M picture. And basically, so what we want to do is we want to kill off the 6-fold symmetries, we want to retain 3-fold symmetries, and we want to retain the triangles within each diagram. So basically here's our sort of central hexagon, let's say. And around it are these 6 3-fold symmetry centers. So we want to only maintain 3-fold symmetry. So maybe we want to keep this one and that one, but we want to transform the other ones into something else that are still 3-fold rotation centers, but are not images of these anymore. And to do that, we have these little kind of flaps around each one. So we can fold over these flaps to just create a slightly different picture and make here, instead of a 3-fold, 3-legged thing, I should have thought of a name for that, like a kind of tripod, we can make this little triangle. I need my iron. An iron is your friend for this job. You can iron these sheets of paper. It works really well. So here, so we want to keep that one the way it is. We want to transform this one into a triangle, a little triangle. So these two are transformed into triangles. The others are going to stick where they are, and this one is going to get transformed as well. So we're maintaining the symmetry of each of these little sort of basic triangular structures, but we're switching every second one of them so that we only retain a 3-fold symmetry and not the 6-fold symmetry that we started with. And the other examples, basically sort of similar kind of ideas, just adjust something so that you kill off the 6-fold rotational symmetry, retain the reflections that you want to retain, and sort of kill off the ones you want to kill. So, I'm not saying necessarily that it's sort of easy to come up with a design that admits these sort of adjustments, but it's a lot of fun and it's quite interesting. And I'm kind of interested in thinking up a few more of them. So that's the examples with 3-fold symmetry. The others are very, very similar. I mean, if anyone's interested later, I'm certainly happy to share those too. Okay, let me go back and mention just a couple more things. Okay, so I thought while we're at it, we might as well have a look at a few of the patterns that have fourfold rotation. So these, of course, are based on a square lattice, not on a triangular lattice. So let me quick run through here. So basically what you discover is if you start with a fourfold rotation center and its image under a shortest translation, then you discover that its images under all translations must form this kind of square lattice. And if you think of the four sort of nearest points here as forming the vertices of a square, then the sort of center points of all those squares also must be fourfold rotation centers. So they come in kind of two types. And a primitive cell will look like one of these squares. And again, you have the same question. What kind of reflectional symmetries can you have? Okay, so of course you might not have any, you might only have rotations. That's a possibility. If you do have reflections, they must be reflections of the system of translations. So there must be reflections of this pattern of red and blue dots. So for example, there's a primitive cell. You could have reflections that pass through the centers of each square. And if you have any of those, you have to have all of them because you have to be able to compose them with 90-degree rotations. So you could have a system of lines of reflection like that. And of course, all their translates through all the tiles. That's one thing that could happen. And that's basically the case where you have sort of the full dihedral symmetry of the square on top of the translations. And that group is called P4M, 4 for the rotation of order 4 and M for mirrors. Another thing that could happen with reflections is, okay, so what other reflections does the pattern of dots have besides the purple ones that are shown here? Well, it has some that kind of don't pass through any of the fourfold rotation centers, but pass through kind of the midpoints of all these squares. Those are reflections of the sort of translation lattice, and they can also be reflections of a wallpaper lattice. So this is kind of the other possibility that has reflections, but lines of reflection not passing through the fourfold rotation centers, and these are distinguished as two different wallpaper groups. So we get 3 of them with fourfold rotational symmetry, one with only rotations, one with the full dihedral symmetry for each square tile, which is that one, and one with this kind of diagonal sort of setup, or whatever you might call it. For this one, I'm going to just adjust the primitive cell by shifting it slightly to the left so that the lines of reflection occur as diagonals of the square primitive cell rather than these kind of lines that cut it sort of through each quarter, just because it makes it easy for the next origami pieces. So here are 3 pictures. So you will not be surprised to learn at this stage that these are 3 photographs of the same piece of paper, taken not very long apart, maybe 20 minutes apart from each one to the next one. So there are adjustments that take us from the group P4M. So there's a primitive cell, P4M, that's square, we can observe. It's a primitive cell in the sense that it's a basic tile that's repeated through its translations and covers the whole pattern. Okay, and this square, of course, has all the symmetry of a square. It has reflections in the diagonals, in the perpendicular bisectors of the sides, and it has the fourfold rotation. Second example, this represents the one where we have a square primitive cell, again, a bigger one. It's kind of increased from the first one. It's doubled in area from the first one. It has axes of reflectional symmetry, which are the diagonals of the square primitive cell, so vertical and horizontal lines in the picture. The center of the square here is not a center of fourfold symmetry, it's a center of twofold rotational symmetry. And the fourfold rotation centers are the midpoints of the 4 sides of this primitive cell, and the reflection axes don't pass through them. So this is an example of what they call P4G. G is for glide reflection, which is another thing that occurs in this group. So it's distinguished from P4M, which is the first one. And then the third one is P4. That's the group, wallpaper group, which only has fourfold rotational symmetry and no reflections at all. And hopefully you can confirm by looking at the primitive cell there that indeed the tile itself and the whole picture has fourfold rotational symmetry, but doesn't have any reflections. And so centers of fourfold rotational symmetry here are the center of this tile and all of its replicas, of course, and also the corners of the tile are centers of fourfold rotational symmetries. So just to highlight this, in case you're kind of looking at these pictures and wondering how exactly they're all the same page, the same piece of paper, these 4 points that are highlighted and all their replicas around the pages, where you have a kind of a cross in the folding, those are the same in each of the 3 pictures. And the same 4 points, I think, more or less are actually highlighted in all three pictures. So we can take those to be sort of points of reference. So if I have a couple of minutes, I'll just finish off by trying to show you how to go from one of these pictures to the other in terms of folding. And this is the third version of this picture. This is the group P4 with just the rotational symmetries and not the others. So in order to go from that one to the first one, basically we have all these kind of crosses, and beside them we have these kind of tabs that again are movable. So we can open out these ones. It's a little bit fussier than the last one. And we can do that for all four of them around one of these crosses. And by doing that repeatedly, all around the picture, we now have something here, this square, if we do, well, see, we want to do it everywhere. So we're picking up some reflections that we didn't have before, and we are also introducing more fourfold rotation centers. We want to do the same here. So we're just opening out all these kind of creases that were tightly bound. So we're kind of moving there from the third version of the picture to the first one. Okay, so there's the sort of basic tile from the first picture that we saw. Okay, and what we do, and so we pick up these little small squares that were missing from the previous picture, and essentially, you know, in going from that picture, so this part of it at least kind of resembles the first version. If you just look at that little square where my fingers are, to get from that one to the second version, which I won't inflict on you at this stage, basically what you have to do is kind of expand these sort of center squares a little bit. These are fourfold symmetry centers again, but we're going to adjust them so that this one becomes kind of a tall, skinny one, and the next one will become a sort of horizontal, flat one. And with that, we can adjust from the group P4, which has rotations and doesn't have reflections at all, to the version P4G, which had the reflection axes in the diagonal of the basic squares. So that's what I have to share with you. I hope you enjoyed it. And I guess the sort of thesis basically is that, you know, origami is a good environment for exploring the relationships between different wallpaper groups, and that it's a lot of fun. So thank you very much, everybody.
Thank you. That was beautiful and impressive and amazing. So let's look at some of the questions. I saw someone ask what kind of paper you use. That was my question as well. Is it a special origami paper?
It is. So I started this from nowhere, really. And actually, I should mention, like, things like the triangle twist, you can do that with a piece of office paper. It'll work quite well. Eventually, it'll start to tear on you, but you know, you can do quite a lot with just an ordinary piece of office A4 paper, or even a page from a notebook. Like, you can do more than you expect. So yeah, this is special origami paper, and this particular paper is called satogami. It's Japanese paper. I guess once I started to get more into this, I started to kind of try out some different papers. There's another one called TANT, T-A-N-T, which I also really like for tessellations. I don't know a lot about origami paper. I understand that it has longer fibers than regular paper. So it means it withstands kind of multiple folding and unfolding better than kind of ordinary office paper does. But actually, but you know, if you want to try out things like the triangle twist, you can absolutely do that with a sheet of regular A4. Cool. And there are loads of different papers. I mean, people who do sort of geometric type stuff like particular papers, and people who do animal models like other papers, you know, so it's there's a lot of stuff out there about paper.
Great. Another question: how did you conceive these highly elegant designs?
Thank you for that lovely question. So I suppose, so I'll tell you what, I mean, I'll tell you how I got into this, although it's not quite an answer to the question. Somebody gave me a gift, which was this book called Origami Tessellations by Eric Gerde. Some people probably know it. And it kind of has the basic moves like the triangle twist, and it has some designs, not including any of these. But I guess I started doing some from the book, and I kind of began to realize that they're kind of infinitely adjustable. And I should say as well, like, all the methods that I'm using in these patterns, you know, to sort of serious origamists would be considered kind of, you know, baby's first steps, the triangle twist and the crease patterns, you know, and the pleats. But I kind of started to realize that you can make kind of infinitely intricate patterns with just these few sort of basic steps. And I think I became kind of fascinated with that, and also with the symmetry patterns. And I kind of started to, so I didn't learn the more advanced stuff because I was so interested in doing this stuff. So I don't know if that answers the question, but I think what happened was I started to do these designs that were kind of, step by step, directed in the book by Gerde. And I just started to realize that you could adapt certain things and you could adjust them and you could sort of change the distance between tiles and you could just sort of start doing a bit more. So it was just experimental, that's all. So yeah, I'm keen to try out a few more versions of this now, because another thing that's quite nice is that you can have two patterns that have the same wallpaper group, but don't look particularly alike. And so that's another thing that I'm kind of keen to explore with Origami. So yeah, and these particular versions that I've used for these moves between wallpaper groups, I'm kind of keen to try out some other patterns for that too. So thank you for that lovely question. I don't think I answered it, but basically messing around on Friday evenings is the answer.
Great. I wasn't counting. Did you take us through all 17 groups?
No, far from it. I should have said that. So only
you have done all 17?
I haven't done all of them. That's still a work in progress.
Yeah.
But I may have done all of them, but not in this project as such. So So yeah, I mean, I've done the ones with the most rotational symmetry, in a sense, the ones with 3-fold, 6-fold, or 4-fold rotational symmetry.
Mm-hmm.
But somehow the others, in a sense, have kind of less symmetry, rotational symmetry at least. Although I certainly have, certainly we can move from these ones relatively easily to some of the ones with fewer rotations.
When you were making those adjustments, going back and forth between the reflection symmetry and non-reflection, Scott Wortman was asking, are all foldings of Euclidean tilings similarly adjustable, or have you folded them in a very particular way?
Good question. So I think no is the short answer, because I have tried to do this and run into trouble where, they're kind of, this is a tricky one, because what you call an adjustment maybe doesn't have a precise mathematical definition, or at least it doesn't yet. Because of course you can always adjust something, but it might be barely visible to the viewer, so all of these, I kind of created them deliberately so that they had sort of particular tabs that you could move one way or the other. And I ran into a little bit of trouble actually in the first examples with the P31M, the one where the two triangles are not reflections of each other, or are reflections of each other, and each of them only has 3-fold rotational symmetry. So to manage that, I had to increase the size of the primitive cell, which hadn't been my intention at the start. I didn't really like it at the time, but it was because I just hadn't built in enough adjustability into the sort of basic primitive cell to allow for all the adjustments. And having said that, you could do it. You could do something that would give you the right symmetries, but it wouldn't be visible really in a setting like this, and you'd be skeptical about what I was claiming, quite rightly. So you want to have it kind of big enough that the differences are clearly visible.
Kate Joan was just asking how she could learn more about the meanings of all the 17 patterns and the vocabulary. And someone said she should read the Symmetries of Things, which I second. That's a fabulous book. You'll find the terminology there is different. It uses what's called orbifold notation instead of this crystallographic notation. And there's debates about what the best terminology is, which you probably have opinion. You were mentioning you have opinions on, Rachel. You said you're not really happy with either of them.
Well, I think I'm not unhappy with them. I'm kind of more used to the crystallographic notation. I guess I think that neither of them are very descriptive to somebody who hasn't actually studied them in detail. So,
Yeah.
So that's all. I'm not unhappy with them, but they're, if you didn't know anything about what they were about, they wouldn't look like the most appealing list of things to learn about, maybe. But all right, I'm looking at the comments. Kate, that's amazing. Puzzles of each of the 17 wallpaper groups. That's fantastic. Can we follow up on that? Sounds fantastic.
CoM has a question here. If you unfolded one of your creations, would it occupy 4 times the folded area? How much would it expand?
That is an excellent question. So as it would have it, my document, my Lightbox has a ruler on the side, although my document camera can't really see it. So yeah, so the side of this square now is 31 centimeters. It started like at 50 centimeters. So I don't think it's exactly a quarter, although some of the designs that I've done would be exactly a quarter. You've probably seen these hydrangeas, these Fujimoto hydrangeas, which I've done too. They occupy exactly a quarter of the original area. These are a bit more because they're slightly sparser patterns, but so this one, the side length seems to be roughly 2/3 of how it started, which is, so I think it kind of depends on how much light you leave, how sparse the folding is.
Have you published your designs anywhere? That's a good question.
No, I haven't. It's only quite recently that I've kind of that I've even spoken about them in any sort of public environment. They're on Twitter. I post them on Twitter all the time, but no. Although I am thinking of trying to write up a paper about this idea. So that's kind of
that would be very, very cool. Yeah, a lot of us would have fun.
Thank you for that encouragement. I appreciate it a lot. yeah, I just like it. I mean, it's honestly, it's my hobby. So if I can combine it with my mathematical work, I'm even happier. So.
Yeah, I see CoM has just shared your Twitter handle there.
Thank you, CoM.
Yeah, good. So thank you once again, Rachel. That was exactly the kind of talk that we look for, combining fun and art and math and hands-on. Just check all the boxes there. So thank you.
Thank you so much, Bob, and thank you, everyone.